Hello everyone. Today I'm going to talk about foundation design, footing design, and especially pad footing design. Pad footing is very common and popular in structures, industrial, residential, or any type of structures. It is the best as isolated from the others, and it's not impacted by the other foundations. Let's go for the aim and the main criteria. The aim for pad footing is generally to transfer the loads from superstructure to a safe ground. Ground should be strong, and the loads are going to be taken from the superstructure and spread to the ground. Ground is soil, rock, or just any type of layers. We have three main criteria. The first one is soil rupture, that we check the stress distributed on the soil or bed. That should be less than the bearing capacity of the soil. The second one is pad itself, that should be capable of the loads applied on that. We generally check for bending and shear. And the last one is punching the slab into the pad footing. We need to make sure that the column is not punching the pad footing. If we meet these three criteria, it means that we have safe design for pad to transfer the loads from superstructure to the ground, and ground is not rupturing, or we don't have any failure of bed soil. In general, we have these values as input to design. We need to have concrete cover around reinforcement in the pad, and we need concrete strength, and we need yield strength of the reinforcing bars. We need loads. Generally it is G and Q, dead load and live load. And we need soil bearing capacity, that is called QA, and in special case we need subgrade modulus, that is easily can be calculated from QA value, or if we want to have just very accurate value, it should be given by geotech engineers. And the last one is just column size, shown here as A and B. We need that one mainly for punching shear calculation. So the output for pad footing will be, we need to size A, B, area of the size, and also thickness of the pad. And also we need to have bar distribution in the section. For this type of pad, we generally have just bottom layer to take tension loads, and in two layers, X and Y. We will talk later more about this one. So in this case, I'm talking about the general rules for footing design, but for the simplification, I have some assumptions here. We're going to talk about shallow foundation. You know that for shallow foundation, we are not considering the cohesion between soil and pad footing. That is generally helpful to take some loads from the structure. And we assume that the pad is rigid. It means that the loads applied on the pad is going to be distributed as uniform stress under and on the soil. And also we assume that it is simple column connection. It means that this column is not taking any bending or shear at this point, and it is just transferring vertical load. And also the last one is just we have centric load here. It means that the load is applied at the center of the pad. It is general, but for a special case, we may have just some modification, but the rules are the same. So the first one is to design pad area. For pad area, we're going to check serviceability limit state, or SLS. It means that we have loads without factor. It is just G plus Q applied on the pad. It's going to be distributed on the soil, and the stress should be less than the bearing capacity of the soil. But remember, we always have one safety factor. That's about 2, 3, or just in some cases for very special cases or different codes of practice, you may have different values, but yeah, you need to take this SF value, safety factor value, times PS or P serviceability on AB. That should be less than bearing capacity of the soil. From this equation, we're going to have AB area of the pad. So you can assign based off the constructability and the limits you have on the site. You can assign numbers for A and B to have the minimum of the area provided from this equation. I will have very simple calculation for this one later on this video. I'm going to have just general talking about the rules. The next stage is to define the thickness of pad. We have the area of pad, what's A, what is B, but we need to define the pad thickness as well. For pad thickness, that is part of checking the strength of this pad against the loads applied on that, we're going to check ultimate limit state, ULS. So we're going to have factors on the loads. From Australian standard, we have 1.2G, 1.5Q, or you may have just referred to other American or other countries. You may have just different load values like 1.4G, 1.7Q, or just any other load factors you may have. Just you need to find PU value. And this PU value is applied on the pad. We already have the area, AB. It gives you the stress under the pad. Q is PU on AB, on area of the pad. It gives you the distributed stress under the pad. To find thickness of this one, we assume that this portion, we have critical points for this load distribution of the stress, that is edge of the columns. If we go for pad, the plan view, we have these edges as critical for bending, and so we're going this part as cantilever parts under distributed load, uniform load, and we will have M value exactly here, and we need to define what is this length and what is the M coming from these loads at this point. And then we're going to have like simple section bending for reinforced concrete, and we can define what is longitudinal reinforcement in each direction. Just remember, we have two ways of X and I. We need to check both ways for bending. If A and B is not the same, and A and B, small a and b are not the same, we may have different values of M for different directions. So we need to check for both directions to have safe design or consider the critical pad. Just remember, if we have two layers of reinforcement, one depth, or let's say dx or dy, should be short and the other one will be long. So if we have M calculated from this, that is uniform load in this length. Yeah, so you know that it should be QL times Q times this L times half of this distance will give you the M value. And if you have that one, it gives you the applied design load. And when you're going to design for reinforcement and depth, it will be M star should be less than phi mu. Mu is the ultimate capacity of the section with reinforcement, concrete section with reinforcement. So if you are not going to have just very accurate calculation, you can just follow this ZASD FSY for mu. And if you start with Z is equal 0.9D, it is very accurate for your estimation to have Z value. So you can go with Z 0.9D to find FAST. You already have AFSY. But the problem is that you don't have D now because you don't know what's the thickness. So for D, as initial estimate, you can go for just maximum of A over 6 on B over 6. You have two dimensions of A and B. Just 1/6 of each. Just see what's that and choose the maximum as your minimum D. Let's say if it is just 400, you can go even for 450 to start your calculation for D. For general depth, depth or thickness of the pad, and from that you can define what's the cover, what's the bar size, and what is the value for each reinforcement layer. Okay, these are general for pad area and pad thickness. The other criteria that is critical in pad design, foundation design, is punching check. For this punching check, we have two main parameters. The most important one is the thickness of pad. That the higher thickness or the thicker slab has better resistance against punching. And the other one is just shear stud reinforcement. If we need to provide reinforcement for shear punching shear as well. So for this one, to check punching shear, we will have dy and dx from slide previous start, that we have different dx and d value because we have two layers of reinforcement and one sitting on top of each other. So the average should be just average of dx and dy, and from there we will have column where we already should have the size of this column, A and B, that the dimensions of the column, and so the punching area should be A. If we say this is A, this is B, punching area should be A plus 2 times of this average depth, and same for the other one. It is the perimeter area in depth of D dot M. So should be the punching area should be like this, D dot M and A plus 2 D dot M and B plus D 2 D dot M, and the depth is D dot M. So it is your punching area, and you will going to check applied load PU against shear in the interface of this concrete perimeter. So if the summation of all this stress against around this part is just more than PU, it means that it is safe. Otherwise, it means that PU is just governing and we have punching problem. So for this one, we need just FCV, or just shear capacity of the shear strength of the concrete. And just say it is easy. You can find from equations from F-C value, or otherwise if you have from tests. That is easy to find. So those are the basic parameters in footing design. So we have a quick example just to get more familiar with the concepts in pad design. Assume we need to design a pad for a column that is 400 by 400 mil, and we have dead load 150 kilonewton, live load 78 kilonewton, and the bearing capacity of soil is 125 kPa, FSY for steel is 500 MPa, concrete strength, compressive strength is 40 MPa, and shear strength is 2.1 MPa. So we need to have what is A, what is B, and what's thickness of pad, and what is the reinforcement in that. So we already have the column size, that is 400 mil in square in each, and equal in each direction. So first one, we need to define the area of pad. For this one, we're going to just add the loads without factors. It gives 150 plus 78 to 28 kilonewton. And if we have safety factor of 2, it means that 2 times 228 by 125. So we will need 365 square meter pad area. From this square, we can have just square pad, or we can have different values for A and B. I assume here, just for simplicity, I will have 1.5 meter for A and 2.5 meter for B. And AB, area of the pad, will be 375. That is more than what we need, 365 minimum. So we say that A is defined, B is defined. And we have 2.5 by 1.5 area of the pad to take that load, and it is okay for serviceability. Next check is strength of this pad. So we need to check for ultimate load, that is for Australian standard, that is 1.2 G, 1.5 kilo, that is 297 kilonewton. And it applies pressure under the slab as 295 on the area, pad area, that is the latest one, 79.2 kPa. So it will be stress under the pad, 79.2 as UDL, uniform distributed load, and we will have two directions, X and Y. In X direction, it will be 1.5 minus 0.4 divided by 2. It will give 105. It means that we will have 105 here, and same for the 105 here, meter here, and the other one is just 0.55. 0.55 and 105 for mx and my. X and y are shown here. So mx will be q, that is 79.2 times 1.5, the long direction. I am distributed in all ways in the other side, either direction, times 105, the length, times half of this length to have bending moment in this area. So it gives 65.5 kilonewton meter per meter of the slab. And for the other direction, we have the same Q times 2.5, length in other direction, times 0.55, times half of this 0.55. And it gives 30 kilonewton meter per meter. So you will have maximum of 65 and 30, and definitely you're going to design for 65.5 kilonewton meter for the pad. So we need initial estimation of the depth to start. So we're going to have maximum of 1.5 over 6 or 2.5 over 6, and it gives 0.545 meter to start. It should be 0.41, just for safe design, or just to have less trial and error, we're going with bigger number, that is 0.5, or even you can go with 0.5 meter. That is very common for pad footings. It still depends on the load value. Here we have big loads, 1.5 and 75 are quite big load for single pad. So then you can start for the rest is just like bending design check, and you can find reinforcement based on D values and the equation we had for just simple bending. The last check here is punching check. As I said, we have 0.45 meter or 450 for thickness of the pad, and we assume that the cover is 15 mils, and if we have 16 mil diameter for bars, we can change it later if we need, but 16 mil and 20 mil are very popular for pad footing. So we will have dx 392 mil. So you see that it is 350 minus half of this one. We're going to just calculate from the bottom. 450 total minus cover 50 minus half of this diameter, because we're going to calculate from the mid layer of this bar, and it is 392 mil from the bottom, the top to middle of this bar. And also dy, we need another layer of reinforcement. It should be 450 minus cover minus diameter 16 minus half of diameter 8, and it gives 376 mil for other D. So we will have D.M as average depth for reinforcement, 384 mil for punching shear check. So for punching check, we have 400 by 400 column, and we need to extend the area 384 in each side. And if we go for plan view, it will be some area like this, 400 plus 2 times 384 in each side, same. So the load is 297, applied load on top. That should be taken by the area or just shear strength distributed on perimeter of this area. So we have 297, that should be 2.1 is FCV here. And definitely we need to have some reduction factor. That is just refer to your code of practice, which one you follow. So 2.1 times 2 means that 1, 2, 3, 4, just they are same. Just you can have just 2, 1168, that is total length here, times 384 times 2. And see if it is okay, it means that you don't have punching problem. Otherwise, you need to recalculate, and the best one for punching check is to increase the depth of the pad. If you can't, you have to provide some studs, shear studs, to take that punching shear. It should be just in all around just this area. Let's say this is punching, this is column, and if you have punching problem, you need to provide reinforcement in all this area to take that punching. But remember, always D is the best option to increase the punching capacity and also helping to have just better strength of the pad against applied loads. Okay, these are the basic rules for any foundation design. We worked on single pad footing design for simplicity, but the rules are the same for all types of footings. Doesn't matter if it is centric or eccentric loading, or just we have one type of loading, or what's the type. It is just point load or distributed load on the pad, or even we have bending on top of that. The rules are the same. We need to check for soil capacity, pad capacity, and also punching capacity. Thanks so much. We will discuss on other subjects in next videos. Thanks for watching. Bye.